Well, good morning. I hope everybody's doing well today. Today's warm-up is going to start out reviewing what we did last time, and then we're going to also review something from the past. So let's see how we did. Stay on your toes, because the bars of equity are in effect. So, number 1. What is that number divisible by? I've got students 12 and 20. Student number 12, what do you say? Okay, student number 20. 2, 3, 4, 6, and 9. Very nicely done. Number 2, what is that number divisible by? I got student number 6 and student number 2. Okay, and I'm sorry, I know student number 2 wasn't here, so we'll go to student number 16. Okay, it is divisible by just 3. And number 3, what is that divisible by? I got students 18 and 19. Student number 18, what do you say? And student number 19. It is not divisible by anything. So, my expectation was you were able to do all 3 of those off the top of your head, and it is my expectation for the next, well, let's just say the rest of your life. You will have no issue whatsoever determining whether or not a number is divisible by 2, 3, 4, 5, 6, 9, and 10. Now number 4, from the past. Which of the systems has the same solution as the given system? I've got students 3, 1, 13, and 10. Student number 3, what do you say?
A.
Student number 1, what do you say?
B.
Student number 13. And student number 10, what do you say? Okay, the correct answer is A. But let's be clear, this was not a guessing game. This was actual work that needed to be done. So we'll talk about that in a moment. So let's address numbers 1, 2, and 3 first to make sure we are feeling comfortable with the divisibility rules. It's going to impact today. Any concerns or questions on 1 through 3? Give me a thumbs up if you got all of them correct. Being 100% honest, leave your thumb up if you were able to do all 3 of them without looking back in your notes. Good, put your thumbs down. If you were able to do that, I'm quite proud. Keep up the good work. Now let's go to number 4. So now I need to survey this one first. Give me a thumbs up if you got number 4 correct. Give me a thumbs up if you got number 4 correct and have work on your paper to support why. Good. So, Paige, start us off. What was the first thing you did? You solved the system, of course. What method did you use to solve this system? Beautifully said. Elimination. And to achieve elimination, what did you do? Nicely done. Multiply the second equation by 2, and that becomes 6x minus 2y equals 18, and then you add down. And what was the result after you accomplished that? What was, after you eliminated, what did you get? 4x equals 16, and so x equals 4. Beautifully done. And so you now know that the solution is 4 comma something. What did you do with the 4 to get the y value? And you got what? So the solution is 4 comma 3. That's the solution of this system. But that's not what I asked for, right? So Amir, I asked for which of these has the same solution as this one. So now you have to go next level. So Paige, from there, what did you do? Of course. course, that makes perfect sense. You've got an x and you've got a y. Plug in x and y, plug in x and y, plug them in, and see where it works. And it only works part A. Now, I've done this lesson with other groups, and I've had other students tell me they took different approaches. Nobody in the class other than one person seemed to be able to achieve success on this question, so I'm not going to be able to pull other approaches out, but maybe you can observe something as you look. There's some connections going on here. Okay, I see your point. So this one looked so different than the rest of them that you just kind of said, that can't be it. Okay, do you see now why it can be it? Not really? Okay, well, I want you to look right here. I want you to look right here. Right here. See how when we eliminated, we actually ended up with that equation? And then look at this right here and this right here. That's the same equation. So this is actually the exact same system expressed in a different way. Remember the analogy I've used all year about money? And what's the question I always ask you guys when I ask about money?
$1 in money is the same thing. $1 is more specific.
Okay, so yes, I use that in that case to talk about words, but then I use money in another situation, another analogy. What was it, Catalina? Right, so there's all these different ways to represent $1, but it all has the same value, right? So this is one way to represent this system, and this is another way to represent the same system. Okay? Questions? Any comments? Okay, so today we're going to take the skills that we worked on last time, and we're going to actually use it for another idea. We have a major overall goal by the end of today, and that is to be able to find the greatest common factor of algebraic expressions. No easy task. Today is going to be a building process. In fact, the building process started yesterday. And basically we're going to continue building until we get to the point where we can get the greatest common factor of algebraic expressions. To do this, we need some terms that we can use. First, let's remind ourselves of two terms, prime and composite. A prime number is a whole number that only has two factors, one in itself. This should not be new information for you, but I wanted to make sure we were clear, because we're going to be using the idea of prime numbers over and over and over again. So here are some examples of prime numbers. 2 is a prime number, 3, 5, 7, 11, there's many more. 13, 17, we could go on and on and on. There's infinite prime numbers. But what is most important is the fact that you see there's only one factor pair that can be used to achieve those numbers. Any questions about that? So what is the opposite of a prime number? The opposite of a prime number is a composite number. So a number is either going to be prime or composite. If it's not prime, then it's composite. If it's not composite, it's prime. What is a composite number? A composite number has more than two factors. So here are some examples of composite numbers. 10, 18, 30, and 20. These are all examples of composite numbers. And you can see clearly the difference. If you look at the table up here and the table down here, the difference is just jumping out at you. 10, 18, 30, and 20 all have all these different factors. Remember, each of these numbers is a factor. That's a factor of 10. 5 is a factor of 10. 2 is a factor of 10. 1 is a factor of 10. Now we put them in pairs, and we call that a factor pair. That's a factor pair. Same thing is true for 18, 30, and 20. So we've established a difference between prime and composite. Any questions? So here's the critical piece. A composite number can be written as a multiplication problem of prime numbers. Every composite number can be broken down so that all that's left is prime numbers. And that's one thing we're going to work on today. So, what is that called? That is called a prime factorization. When you take a composite number and rewrite it so that it is a product of prime factors. Boy, we got some fancy language going on here. Product, prime factors. So here's an example. 2 times 3 times 5 times 5. When you multiply that out, you get a composite number. So one of our goals today, one of our intermediate goals, is to learn how to find these. That's not our ultimate goal, but that's an intermediate goal. It's another skill along the way. So how do we find a prime factorization? There's a bunch of different ways. By the end of today, I'm going to hopefully have imparted to you a very high-level technique for doing it. I'm working right now with a group of very high-level students. I'm going to help you see a high-level approach. But to get there, we need to do something a little bit more rudimentary. So, a factor tree can be used to find a prime factorization, and here's an example. You start with something got messed up. This is supposed to be 40. I apologize for that. I don't know what happened there. So we start with the number 40. If we would like to know the prime factorization for 40, it's 2 times 2 times 2 times 5. At this point in my life, I can do that without drawing a tree. But when I was younger, I started out learning a tree. And what we do is we figure out a factor pair for 40. We put one number at the end of one branch and another number at the end of another branch. And any number that's prime, we circle and we close the branch. So that's a prime number. That branch is now closed. That's not a prime number. Now we find a factor pair for this number. 2 times 10. 2 is prime. We close the branch, but 10 is not. So now we do another factor pair of 10. Now 2 is prime and 5 is prime. And so the prime factorization for 40 is 2 times 2 times 2 times 2. I'm sorry, 2 times 2 times 2 times 5. Or, if you're super fancy, you write 2 to the 3rd power times 5. Mathematicians want it like this. You will see today that there are some benefits to leaving it like this. So I am okay with it either way. I am okay with it either way. Which brings us to our ultimate goal. And again, if you're copying every word, if you're copying even more than half the words, then you're making a mistake. Here's our ultimate goal. It is to be able to find the greatest common factor. And so we're going to take all of the skills from yesterday and the skills we're going to build today to apply to this. Because this is the critical idea moving forward. If we find the prime factorization of this expression, find the prime factorization of this expression, we can use that information to find that. That right there is the GCF, the greatest common factor. It's the greatest common factor of these two expressions. And that is our ultimate goal. I'm sure you have lots of questions, lots of concerns. They're going to come up throughout today. Please feel free to ask. During checkpoints, consult with teammates to see what's going on quietly. If it's a team activity, then you immediately start discussing. But we're going to start out working individually, and again, we're going to be building. Any questions? Any pressing questions so far? If you're missing something from this, leave a couple of lines of space in your paper and continue Let's start with finding a prime factorization. So, we're going to find the prime factorization, and the work we're going to do is called a factor tree. I am going to do 2. You are going to do 1. I am going to do 1 in blue, and I'm going to write 1 in green. I want you to choose right now which one you're going to do, blue or green. I don't really care. Pick one of them. So, what I need, and you may not use your calculator at all, is I would like a factor pair for 420. 1, 2, 3, 4, 5 people right away. Tyler.
2 times 210.
2 times 210. You got another one? Cheyenne? 5 times 84, you sure? How'd you figure that out? Okay, thank you. I appreciate that. Okay, so 2 times 210, and Paige, what was yours? 10 times 42. Okay, so we've got 2 times 210, and we've got 10 times 42. I don't care which one you're doing, but pick one and stick with it. Now we are working across. So you are now looking not at the top level, you're looking across this level, and you're looking to see if any of those are prime numbers. Are there any prime numbers that I need to circle? Any prime numbers? Chanel? 2 is a prime number, so that branch is now closed. No other prime numbers, though, which means all the other branches are open. So that means that I need to branch off from here, and then I'm going to branch off from here. I'm going to branch off from here. Let's start with 210. Can I have a factor pair for 210? Amir? Okay, Garion? 2 times 105, and what was yours? 10 times 21. So it doesn't matter. That's the whole point of me doing 2. You're going to see at the end. So we've got 10 times 21. And now I need a factor pair for 10 over here. Yasmin? 2 times 5. And I need a factor pair for 42. Michael? 2 times 21. So now we are looking along this level for prime numbers. Any prime numbers on this level? Anything prime? Amir?
The 2s are green.
Okay, the 2s. Anything else prime? Okay, Shabay? The 5, also prime. That's closed. Anything else? Good. So now we're back. I need factor pair for 10. Oh, wow, look, I got it right there. Already did it. 2 times 5. But I need a factor pair for 21. I don't have that. Caleb? 2 times... Okay, yeah, it's not divisible by 2. That's why we got those rules. Jesse? 3 times 7. And since we have a 21 over here, I can use that same factor pair, 3 times 7. So, any prime numbers that I can circle? Any prime numbers I can circle? Amari? 3 and 2. Any others? Paige? Everything is now prime. Now watch this. What we were looking for was the prime factorization. Watch this. 2 times 2 times 3 times 5 times 7. 2 times 2 times 3 times 5 times 7. No matter which path you take, you get the same result. 2 times 2 times 3 times 5 times 7. That is the prime factorization of 420. Or you could write 2 to the second power times 3 times 5 times 7. So I told you to do it one way. I did it 2 ways to illustrate that it doesn't matter. As long as you do your multiplication and division properly, you get the same result. Kayla?
When you write the prime factorization, should it go from greatest to least or least to
Based on what I've done, what do you think? Okay, so we want it from least to greatest, and you will see why in a little while. Very good question. Excellent question. Any concerns about what you're seeing? Good. I'm never doing it 2 different ways ever again. From now on, I will do it one way. Let's do the prime factorization of 102. See, your brain should immediately be going, oh, it's divisible by 2, it's divisible by 3, it's divisible by 6. Should just be popping right in your head, right? What is it divisible by? What is 102 divisible by? Gary? Yeah, it's divisible by 2 and 3, which means it's also divisible by 6. Oh, look at that. So, pick a factor pair. Don't use a calculator, do it mentally. Stick with the easiest thing you can think of. Cheyenne? Beautiful. 2 times 51. Prime number. Circle it. That branch is closed. 51. What's it divisible by? It's a strange number. Yasmin? How'd you know that? Ah, yeah. It's divisible by 3. Look at that. So 3 times what? 3 times what? Now you're going to have to do a little mental math. Am I right? 3 times 17. Prime numbers. Circle them. 3's prime. Anything else? You dash? Yeah, 17 is also prime. So we're done. The prime factorization of 102 is 2 times 3 times 17. Any questions on how we achieve that? Any concerns? Good, we're doing quite well. Nothing at all? All right, let's see how you do on your own. You got 2 that I'm asking you to find. You got 3 minutes. If there's still time left, compare your answers and your path to your teammates.
We're independent. Would you? Oh, for the second, yeah.
All right, seems like I may have overestimated the time, so I'm going to cut the time. So let's see how we did. All I want to know is the prime factorization. So for part A, I've got student 6 and 10 and 2. Student number 6, what do you say?
I believe that it is 2 squared times 7.
Okay, student number 10. Okay, student number 2.
2 squared times 17.
2 squared times 17 or 2 times 2 times 17. I'll accept either form. And part B, prime factorization of 40. I've got student number 21 and student number 16 and student number 18. Student 21. Okay, student number 16. So 3 students agree that it's 2 to the 3rd times 5, or 2 times 2 times 2 times 5. Any concerns so far? Concerns? Any observations? Any theories? So we are still in the building process. So now we go next level. What if I asked you to give me the factorization? It's not really called a prime factorization because now we've got algebra involved, but it's basically the same thing. So the first time we're going to do this the long way, and then from there, hopefully you will have observed and kind of started seeing things a little bit differently. And from there, we'll hopefully be able to develop an even more effective way of doing this. So we start out with 12x squared y. And we would like the factorization of that. So what we're going to do is we're going to separate the coefficient from the variables. So because this is a multiplication problem right there. So the first factor pair is 12 times x squared y. That's the first factor pair. Right? Because if I multiply these two together, I get that. That's what a factor pair is. Two things you multiply together to get a result. Now, prime only applies to numbers, and so we don't have to worry about that with this. So let's just stick with the numbers. Can I have a factor pair for 12? Factor pair for 12, Caleb? 3 times 4. Anything prime? Tristan? 3. 4 is not prime. I don't know if I really need to call on anybody. 2 times 2. And so we can see that the factorization is going to be 2 times 2 times 3 times something. So now we have to break this down, and it's unbelievably easy. This is a multiplication problem right there, right? X squared y. Right? If I multiply x squared times y, I get x squared y. Y, it's not prime, but is there anything that we can multiply together to get y? No. So that's closed. What about x squared? What do we multiply together to get x squared? Chanel? Very good. We get x times x. And those are now closed. And so now we have everything we need. Put it from smallest to biggest, and you put the variables by themselves in alphabetical order. So we get 2 times 2 times 3 times x times y. My hope is, in 1 second, Tristan, my hope is that that will be the last time you do a factor tree. That's my hope. The factor tree is a training wheels technique. So I've talked to you about this before. You take off the training wheels when you're ready. I think that most of you should be ready. If you're not, you can always use the factor tree. It works every time. Okay, Tristan, what was your question? That's what we're going to talk about right now. So now that we've seen it, and now that we're super bright, we can use our minds creatively. So now we're going to factor 18a squared b to the third. But we're going to do it differently, and I don't want you to do anything. Don't start writing the answer, even if you think you know. Okay? Got 18a squared b to the third. Now I'm going to ask you to do some creative thinking, using your imagination. I would like you to try and think of a time when you saw a movie. I want you to think of the opening credits and the title screen. When the title of the movie appeared on the screen. Bless you. Have you ever seen a movie where the title of the movie slowly just appeared on the screen? Even if you don't remember, my guess is that you have. Sometimes the title kind of scoots in from the side and then shoots out the other side. Sometimes it drops down and then drops down the bottom. Sometimes it sparkles in. I mean, they got all sorts of special effects that they can use. But the first one that really was used was called the fade in, where all of a sudden it just kind of slowly appeared. And then what happened after that? Slowly disappeared, right? That's called the fade out. So I want to use the fade out and the fade in. So here's what I want you to do. I want you to look at the number 18. And in a moment, I'm going to ask you to close your eyes. Don't do it yet. When I ask you to close your eyes, I want you to put in your mind the number 18. Don't do it yet. And what I want you to do is I want you to force the 18 to fade out, meaning it disappears. And I want in its place to fade in a factor pair for 18. So in other words, I want you in your mind, the 18 is going to slowly disappear, and two numbers multiplied together is going to appear. So I'd like you to close your eyes, and I would like you to make that happen. Go. Okay? Good. Open your eyes. So what factor pair appeared? What appeared, Marcus? 6 times 3. Anyone have something else appear? Laurel? 2 times 9. Anyone have something else appear? Cheyenne? 1 times 18. So I'm glad you brought that up. That's the one that we don't want. We never want to use the 1 if we're trying to find a factor pair. So now we're going to come back to this question. Now I want you to put the number 30 in your mind. I want you to put we're going to come back to this question in a moment. Let me back up a little bit. We'll come back to this, and I want you to put the number 30 in your mind. And I want you to do the same thing. I want you to fade out, fade in. What appeared in its place? What appeared in its place, Udash? 6 times 5. Anyone have something else appear? Jesse? 15 times 2. Anyone else? Amir? 3 times 10. Okay? So now I want you to watch. Did it look like this? So now I just demonstrated what I was hoping you were envisioning in your mind. But here's the thing, and this only works for very bright students like yourselves. We're not done. What's prime and what's not prime? Someone tell me what do we have going on here, Tyler?
The 2 is prime, but the 15 is not prime.
Okay, so now we need to make the 15 fade out and something else fade in. Okay? So now I want you to do it. Go ahead, and you don't have to close your eyes. If you want to, go ahead. Make the 15 fade out and something else fade in. What faded in its place, Kaylee? Now everyone look up here. Did it look like this? Okay, so what I'm asking you to do is use your mind creatively. And so now, So now what we can do is instead of doing the factor tree, we just did it mentally. So now let me go back to the original. So now we've got 18a squared b to the third. And you guys told me before that you faded it out, faded in. You had a couple different answers. I don't care what you used. So some of you said 3 times 6, and some of you said 2 times 9. Stick with it. Okay? I'm going to use 2 times 9. So right now, in my mind, I've got this. Oops, excuse me. In my mind, the 18 faded out, and in its place appeared 2 times 9. One of those numbers is going to stay in my mind, and the other one's going to fade out and get replaced. What's going to fade out? What's going to fade out, Alex? The 9 is going to fade out, and what's going to replace it? Say it again. 3 times 3. Okay. So now the 2 times 9 is going to, the 9 is going to fade out, and it's going to get replaced by 3 times 3. I didn't really leave myself enough room, but hopefully I can make it happen. So that fades out and gets replaced by a 3 times 3. And so I just did the factor tree using creative thinking. So Tristan asked earlier, can we just skip over all of this? So what's the answer to the question, Tristan? Yeah. Not only can you skip over all of this, you can skip over all of this using your mind creatively. So we took care of the number. Now the letters. How many A's am I going to write out? Let's see who can figure that out. How many A's, Marcus? 2 of them. How many B's am I going to write out? Yadesh? 3 of them. So factoring this expression is going to be 2 times 3 times 3 times A times A times B times B times B. Does anyone have any questions about the approach that we took? Paige, Yasmin, Tristan. No, you're going to see why in a little while. Just stick with me. Remember, it's a building process. You're going to see it in a moment. Yasmin? Same thing? Okay. So the point is to be able to see that A squared is A times A. When I turn you loose to try things on your own, then you use whatever technique you want. Some of you are even higher level than I'm treating you as. Okay? Any questions about either of these? So now let's see what you can do on your own. Factor this. I think 1 minute is sufficient. If there's time left, compare your answer with your teammates. All right, let's see what kind of success we had with this, keeping in mind that we are still building towards our goal. We haven't even reached our goal yet. So, what is 33x squared y squared z squared when you factor it? I've got student number 4, 12, and 6. Student number 4.
3 times 11 times x times y times z.
Okay, student number 12. Okay, student number 6.
I agree.
It is 3 times 11 times x times y times z times z. Any concerns? As I've said several times, that's not our goal. That was an intermediate goal. Now the real goal. The real goal is to be able to find the greatest common factor. You don't have to write anything. This is just a refresh. So, factors shared by 2 expressions are called common. So I told you you didn't need to copy this, but I would like you to look at the 2 lists of factors. I've got the factors of 12 and the factors of 32. I would like you to identify the ones they have in common. Give me a thumbs up when you've got all the ones they have in common. Okay, Catalina, what do they have in common? 1, 2, and 4. Which one is the greatest? Which one is the greatest, Keshope? 4. The GCF of 12, the GCF of 12 and 32 is 4. That's finding the greatest common factor. So what we needed was all the factors and all the factors, but there's another technique that we're going to use to do this. Any questions on what we're looking for? So now let's go ahead and learn how to do it in an effective way. We would like the GCF of 160. So when we're done, I want to be able to say the GCF is, and I would like to be able to do that. So we're going to start out with the numbers, and I'm going to ask you to use the technique that we learned just now. I'm going to give you a moment, and I want you to look at the number 100, and I want you to try to use the fade out and the fade in technique. Some of you may be thinking of it differently already. That's fine. But you got to keep going until it's all prime numbers. Then do the same thing with the 60. Okay? So I'm going to give you a minute to see if you can do that.
In the cafeteria. We'll sell them in the morning.
All right, thank you. Thank you very much. Just leave it out, guys. All right, let's see if we were able to do it, and it's okay if you make a mistake along the way. It's not a big deal. It's part of the learning process. Let's start with the number 100. Give me a thumbs up if you think you were able to use the technique to get all prime numbers. Few people? Not? You weren't able to do it? Using a different way? Oh, okay. Okay, Chanel, what did you end up with? Hold on, I want to make sure everyone hears. Go ahead. 2 times 2 times 2 times 5?
2 times 2 times 5 times 5.
2 times 2 times 5 times 5. Okay? So you think that the prime factorization of 100 is 2 times 2 times 5 times 5? Give me a thumbs up if you agree. Okay?
I thought we were supposed to write like the. I thought we were supposed to write down remember what we did? Oh yeah, that highlighting.
That's what I just did. So I apologize if I confused you. I said use the fade out technique to get all the prime numbers that multiply to that number. Doesn't matter. So don't worry about it. You'll catch on in a moment. What about for the number 60? What does that turn into? Guys, you got to stick with me. Try to, because some of you jumped ahead and you did something different, which is fine. I don't care how you do it. I already had someone tell me, no, they didn't do it at all. They just used a different technique. That's fine. The problem is the next step, you're going to be lost. So you should have trusted my process a little bit more than you did. Sometimes I say, go ahead and do it however you want. Sometimes I need you to trust my process. So this is the prime factorization of 100. This is the factorization of 100, and they're all prime numbers. I need the same thing for the number 60. Gary?
2 times 2 times 3 times 5.
2 times 2 times 3 times 5. I know he's right because I can do that mentally. 2 times 2 is 4, times 3 is 12, times 5 is 60. But our goal is to get the greatest common factor. So watch this trick. Pay attention, because if you're not paying attention, you're going to miss the whole thing. The whole thing we've been leading up to. Find the prime numbers that they have in common. They have a 2 in common, they have another 2 in common, and they have a 5 in common. Multiply 2 times 2 times 5. What do you get? What do you get, Amari? 20 is the greatest common factor for 160. This is the prime factorization of 100. This is the prime factorization of 60. If you find what they have in common and multiply them together, then you get the greatest common factor. So I understand that this is a different technique here that I was showing you. The purpose here was to explain what a GCF was. This wasn't necessarily, because how do you make this list? How do you make that list and make sure that you've got all of them? What if I give you the number 420 and I ask you to make the list? Are you going to be able to do that? No, because there's no way you're going to be able to get every factor. There's no way. There's no way. And there's no point. Because what we're looking for is the greatest common factor. So this is an impractical method. This is a very practical method because it works every time. So I'll prove it to you. Now that you understand what I'm talking about, we're going to do it again for 26 and 52. What I'm asking you to do is use the fade in and fade out, the fade out and fade in technique. That's what I'm calling it. Whatever you want to call it. It's basically finding the prime factorization of 26. Then do it again for 52. So I'm going to give you a minute to do that for both of these. Split that into two. We're done. Okay, so what does 26 turn into? What does it turn into? Laurel? 2 times 13. What about 52? What does that turn into? Yadesh? 2 times 2 times 13. Now, which factors do they have in common? A 2 and a 13. Multiply 2 times 13, and someone tell me what is the GCF, the greatest common factor, for these two numbers. Laurel, you're on a roll. Go for it. 26. Anyone have any questions? Tristan.
I also found out that 26 times 2 is 52.
Okay, so in this case, there was an easier way to do it, but there's a purpose behind what I'm doing, and you're going to see it right now. The entire lesson has been building up to this right here. There's no checkpoint now. Now, this is the whole point. Every single thing you've done over the last 2 days has been building up to this. We're going to do the exact same thing. 15x to the third and 9x squared. I want this written out as a product of factors, and I would like all prime numbers and all the letters separate. So just like we did a moment ago, what would 15x to the third turn into? And the reason I'm not giving you a minute is because mentally it's not hard. Tyler?
5 times 3 times x times x times x.
Very good. So we'll start from lowest to biggest, times x times x times x. Now do the same thing for 9x squared. What does it come out to? Paige? 3 times 3 times x times x. Our goal is to get the GCF of these two expressions. So now find the factors that they have in common. They have a 3 in common, they have an x in common, and they have another x in common. Multiply those together. You multiply 3 times x, and you get the GCF. What is the GCF? Cheyenne? 3x squared. I know that's a little anticlimactic that all that time you spent was just for that, but had I just tried to do this with you from the beginning, you would have been lost. You wouldn't have had any idea what I was talking about. It wouldn't have made any sense. So we had to lay that foundation. Here's another part that's going to be important next time I see you. Look at what's left. 5x is left and 3 is left. That's going to be important next time. So any questions about getting the GCF? So let's make sure we're understanding, and let's do one more. We're going to skip over part C. So we'll stack them up. 8x squared and 7y to the third. And split it up. Split it up so that it is a product of all its prime factors and all its variables. What would 8x squared turn into? Got 3, 4 people. Amar?
2 times 2 times 2 times x times x.
Beautifully said. 2 times 2 times 2 times x times x. What about 7y to the third? Yasmin? Very good. Now, she said 1, and that's correct. There's nothing else to do, but we usually don't write the 1. But in this case, it's actually kind of important because there's actually a 1 up here as well. We'll come back to that in a second. And so now find the numbers that they have in common. They've got a, they have nothing in common. So the GCF of these two expressions is 1. Because the only factor that they have in common is 1. So, I did have a checkpoint that we were going to do, and I had another example we were going to do. I'm running very low on time, so I want to wrap up properly. So, the building process, hopefully you see it now. Eventually, you will be able to look at these two and mentally figure this out without doing anything. That's the ultimate goal. Any questions about that? All right? Excuse me. Your homework. is page 375, numbers 1 through 16. And you will have a quiz next week. And that will be on 7. I'll tell you at the beginning of the week. We also have testing next week. You have your